So basically, have we covered everything in here? Anyone can answer me? Just a small test. What we covered last week? Huh? Include what? I know, searching algorithm, that's a big title there. But how many components we have covered so far? To A-star algorithm, right? We also talk about what company used A-star algorithms. Google, right? The Google map, the one called graph theory, that is A-star algorithm search. And basically they are underlying the tree or graph search. And from today, we will cover the other two types of searching algorithm. Okay, one is simulated annealing, genetic algorithm. And since some of you might know machine learning, deep learning. Why? In what scenario we can use these different type of algorithms? We could not use deep learning. In what scenario? Just guess. Remember, two drivers make deep learning so powerful. One is compute, the other is data. So one reason that why these algorithms they are so powerful, still so powerful in some scenarios, some applications that we don't have much data. Then we can use this type of algorithm to solve it. Okay, still in some scenario, we still can use this different algorithm to solve it. Okay, only when you have data and you have good data, only on that context you can use these powerful deep learning architectures, deep learning models. Okay, okay. So except the Google Map, anything else you can think of that we can use searching algorithm, especially the searching algorithms we discussed last week. The searching, as long as you can formulate that as a tree, as a graph, then you can use this type of searching algorithms. What any applications you can think of in real world applications? Anything? Because algorithm methodology, only when you know how to use it, then it's useful. Otherwise, just tool. What do we want? We want to use this algorithm to solve our problems. So think about, if we have this tool in our hand, what kind of applications can use them? Fundamentally, we want to solve problem, right? We want to make good decisions with our learned methodology. So since we have covered several different searching algorithms, any application scenario you can think of, we can use it. I just give you a problem, then you can probably can use some algorithm, or probably can just tune a little bit to adapt to solve your problem. Anything. You can use ChatGPT, of course. Or you can just think about it if there's any. Robots, of course. Planning, right? You can plan a optimum path. So in here, I list some applications, especially logistics. There are still some companies like Uber, Didi, Amazon, this route planning that can use the searching algorithm to find the optimum solution, optimum path, right? And still compute networking. Any of you have studied computer network? That is one basic course in undergraduate, right? I think some of you from computer science. Then there are some networking problem. You can use searching algorithm. And also games, we have talked about this before. From one state configuration to another configuration. Just design the game, how to play the game. And of course, the navigation, transportation, we talked about Google Map and the robots planning, right? So these are bunch of applications that you can use this searching algorithm. In here, I also want to talk about, this is one of my work in my 10 years ago when I did my master. So basically, you can see this is a familiar the building at the PolyU. This is lots of dots. Each dot represents a sensor. So we can use sensor to collect the vibration data of building. The vibration data is very tiny, right? But still, we can use a sensor to track the data. So we have a time and the spatial data of this building. Given this bunch of data, we can use this bunch of vibration data to detect if there is any defect in the building. This is used in structural health monitoring. Use distributed wide sensor networks for structural health monitoring. So given this kind of scenario, what objective I am going to achieve? First of all, of course, you need to be accurate to detect where is the defect, where is there is any places, something that you need to fix, right? Health detection. And remember, this is wireless sensor. We do not have power to connect to a sensor. The battery usually is very limited. But the sensor, they need to transmit data. Based on this collect data, we need to do compute. So the other objective is that we want to minimize the communication cost among this sensor network. And we want to minimize the compute in sensor computing. Okay, so we have different objectives to achieve. In here, we design a shortest path tree to collect this vibration data. This is one of my paper 10 years ago. Okay. So searching algorithm is still very useful in different areas. And that time, we haven't talked about deep learning yet. Because deep learning, if you remember the history, start popular since 2015 around, right? At that time, we still have this kind of old AI algorithms. Use shortest path tree. This is one of my existing work, one application scenario. All right? And so still, we talk about searching algorithm. We have mentioned, remember, around five algorithms. We have a starting state, initial configuration. We have our target. And of course, we have our objective function to optimize. Either you want to get the highest one or lowest one, minimum, maximum, right? You will have your optimization problem. Then you do optimization. All of these searching algorithms, basically they are doing optimization. So right now in here, that is another type of optimization, something that is familiar in a mathematical courses. Remember, in here we have two-dimensional variable, x and y, two variables. Our outcome is the z in here. So with this landscape, you can think this is our objective function. There's somewhere we can achieve maximum value of z. We can achieve the lowest value of z. But how to get there? This is the optimization problem. So given this kind of problem, what's the solution? If you encounter this kind of problem in your mathematical course, what's the solution for achieve this optimal solution? What's that? That is math. We haven't talked about AI. How to solve it? With this function, with two variables, how to get the optimum? What's that? Gradient. And which gradient equal to 0. Remember that. Let's take a look, okay. That is mass, right? Take gradient, and we take that is equal to 0, and we achieve the corresponding x and y value to achieve the maximum and minimum value. That is mass, right? Okay. So if this one dimension of x, we just simply take gradient. We treat that equal to 0, then that is 0. We can achieve the corresponding variable that can achieve our minimum in this particular problem, right? This is one way, taking gradient and find the variable that is gradient equal to 0. And we can also do a naive way. This is our objective landscape. This is our variable. We can try one step by one step. Discretize the range of variable and try. Just try, right? Step by step. Because right now we're going to achieve the minimum. We try at 0, x equal to 0, we can get one objective function equal to 0. We get x equal to 1, then we get f equals to 1, so on and so forth. We found that as long as we increase the x, the f will be increased. So we will just say in here, we've seen some constraints. We say that x equal to 0, we can achieve the minimum value of f. Of course, you can keep trying, right? But still, we have limits. Example, the number of iterations, because we have limit computation. Of course, here is just a very, very tiny example. You can see we can calculate, right? What about this one? Assume before just have one variable, x. You can try. If we have 1, 2, 3, 10 variables, and each of them, assume the range is from 0 to 10. You can right now just test integer of x1, x2, x3, x2, x10. And for this objective function, I'm asking you to find a minimum value of f. What can you do? If you just do the same try, how many times you need to compute? How many times? How many times? For one variable, we have 11 possibility, and we have 10 variables. Assume it takes 0.01 second to find f for each combination. Then we need 3,002 days. That is 8.22 years for this calculation. Of course, you can use up lots of computation if you want, and in parallel, you can do that. But who is going to do that? Of course, we don't want, right? That's why we will need to figure out more smart optimization problem solution. This is just brain force, not practical. Okay. So conventionally, look at this gradient-driven search. Okay, we have this function f as our objective function. P is our variable. We want to find a P that can minimize this objective function. This is one portion of the landscape. It probably can go up and down. Remember last week, what algorithm is pretty similar in this one? How to get there? This is one called single point search. We just search this variable one by one step based on the gradient. We assume we're starting from here. We take the gradient, take it in this direction. This is the gradient direction. This is the step size to test. What is the next to test? This is our current state. This is our neighbor state. Remember, you can see the idea is pretty similar. Which one? Which one? Informed search. Which one? Exactly. Here climbing. You search from neighbors. This is your heuristics, your guidance, and step by step. Here, the guidance is a gradient of the objective function. You just search by search. And this is the step size. Example, you can get starting from here. Step size means how large step we're going to cross in here. So you can imagine if you have a larger step size, it probably will be unstable. If you have a small step size, too slow. This is also one core of gradient descent. Gradient is one core of doing deep learning optimization to searching the model parameters. Okay, you can see the idea is also similar with hill climbing. So this is how research push forward. They do not start from scratch. Usually they will have inspiration from somewhere. That's why we're reading papers and we discuss papers and we take inspiration from papers. Take the idea from inspiration from the papers. Okay, but why? That's why reading papers is a very good skill that you need to master. Whenever you have a problem, you can try to find your solution from the papers, from the ideas. Even though this is a gradient-driven search, our previous one hill climbing, basically, this can be seen as one type of hill climbing, but specifically use gradient as a guidance, right? So still, we will have the limitations. Because you are taking gradient, you need to make sure it is differentiable. You can get the gradient, right? And the same with the hill climbing. You are easy to get into local optimum because it probably will stop in somewhere there. You think that is a good solution, but it's probably just a local optimum. This is the same limitation as hill climbing, okay? And it also depends on the starting point. If you take as the starting point Pn, if you have a good starting point, you're probably easy to get a good solution. Otherwise, you have to keep calculate gradients towards a better one. So this is some limitations of this gradient-driven solution. Basically, gradient-driven solution is very, very commonly used in optimize the model parameters of deep learning models. Okay, because we haven't get into deep learning. So in here, just introduce, there's a one gradient-driven search algorithm that can optimize something. That something can be deep learning model parameters. Okay? And so in here, we will get into the simulated annealing. The next one, another very useful optimization algorithm, but still it is not deep learning, but it's an algorithm that get inspired from physics. Have any of you heard about physics-informed deep learning? Physics-informed neural networks. So if you remember in our first lecture, one slide we discussed about if AI is science or engineering. Remember, one bullet I mentioned there is we say AI is a science because we need to embed physics, the physical world in the model so as to make it powerful. This is one thing that is physics-informed. That is for deep learning. But in here, this one old AI also inspired from physics. So let's look at what is simulated annealing. The main idea is to avoid local minimum by accepting moves towards solutions probabilistically. This is stochastic. Remember, when you're using hill climbing, when we talk about this gradient-driven search, we search based on the guidance from neighbors, and we compare with our current states with the neighbors. As long as which one's better, we can just replace it, right? We just move our state into next one we think is good. But the problem is both hill climbing and the gradient-driven search, they are both easy to get into local optimum. So this is how simulated annealing comes out. Want to avoid this local minimum, local optimum. How to do that? Trying to accept something that is not as we think that is good. For hill climbing, when you compare a neighbor, we always accept as long as it is better than our current states. But if we find out it is not as good as our current state, we still have the probability to accept it, to move our next action. This is the basic idea of simulated annealing. If you think of this curve, the landscape, if you continue to get the optimum, right? It's stuck there. But in somewhere, you just accept the worst action. That can help you to get from the local optimum. Okay. So let's take the idea come from. It is physics annealing. That is a process for obtaining the minimum energy state of a solid, whereby the melted solid is slowly cooled down until it reaches its ground state. So there one information, one is minimum energy. You can think of this is our objective function. We are going to go to some stable state, our goal state. And we melt the solid, slowly cool down, slowly. We're doing something slowly. We change something. So there's a specific schedule to use to cool down. There's a hyperparameter we're going to tune to schedule this cool down process. We'll see how this simulated annealing mimic the process of physics annealing. Okay. So let's take a look at this major policy algorithm, which is a simulation for the physics annealing process. Okay, so far so good? So far so good? Today we have some mathematics. We have some proof there. So far so good? Make sure you understand the idea first and every piece of information. Okay? If not, just interrupt me and ask. Don't be shy. So the major policy algorithm. This is proposed in 1953. We have a sequence of states, and still we are doing search. So we have the current states as I, and the next states. We have our objective function. In here, it is energy. Then we want to mimic the physics annealing. So we have the energy. Whenever we have the state, we can calculate what is the energy. We want to find the target state that with a minimum energy. This is our target, okay? So if the next state, EJ, smaller than the current state, we accept it 100%. Fully accept this state. That's we will want to move the next state, right? Otherwise, not like hill climbing, we will accept the next state, even though it is not the smaller energy. This is the main contribution of this simulated annealing. They involve a probabilistic to accept the worst action or no. You can see this is energy, the gap of energy, and there's a Boltzmann constant. This is a constant, and this is temperature. This temperature we can tune. Hyperparameter we can change along the way. At the beginning, we can get a higher temperature, get slowed down quick. But when we approach the equilibrium state, we can slow down by adjust the temperature lower to slow down the cooling down process. So this is the basic idea of this probabilistic. Okay. So if the temperature is lower slowly enough, the solid may reach thermal equilibrium at each temperature. So in here, we have the current states, we have next states. These are variable. We need to check. And we check the energy. And along the way, we compare to see if we want to move the action or no. If we want to move to the next step or no, based on the policy. If this model, of course, we accept it. If no, we just calculate probability if we want to accept it or no. Okay, there's a chance to accept the state that is worse. Okay, this is the best idea. So go back to the more rigorous notations. We have a bunch of candidate solutions. We have the solution, we can calculate cost function. The cost function, you can treat that as our objective function. We need to compare the energy. We just mentioned the same thing, okay? And we have the neighbor we need to compare to make our next move. And whenever we have the state, we just generate the neighbors. We calculate the cost function. We accept it. It is as long as it is better. Otherwise, we just make a decision based on a probability. If that is a worse move, okay? And we can change the controller parameter T. It is one application dependent parameter. For each application, the T, they're different. Okay, just like deep learning. Later on, we introduce, there are lots of hyperparameter you need to tune. Okay, okay, still, here's one. That is parameter temperature T. Okay, so far so good? So far so good? So silent. What's that? Okay, so is that good? Yeah, you can. This is just so core here is here. You can connect the hill climbing algorithm. The one main difference is that we involve probabilistic, right? To accept this move or no. That's the main difference. Because hill climbing, whenever we have a neighbor, we have neighbors, right? Just compare to figure out the best one and make our next move. But in here, we have a chance that we accept the worst move based on the probability we calculate in here. This is the main difference. That's it. So the parameter will affect the probability in here. So in here, this is the next state move. This is the current state move, right? The cost function. And then the T here. We base on this probability if we want to admit this worst action. That's it. So this is how we control the T. These are the main parameter we need to tune in the algorithm. It is application dependent. So far so good? Huh? Let me show you the pseudocode in here. Okay. So this is more computer science people, pseudocode. Okay. So we have an initial state, our starting point. And we have the initial temperature, usually the larger at the beginning. And while we haven't got the equilibrium, this is our target goal, target state, minimum energy, right? And we choose the neighbor of the current state. And we calculate the gap and see if that is make our energy smaller. If that is smaller, then we admit this move. We move the next state into a neighbor, right? S prime. Otherwise, for hill climbing, we just skip in here, right? We just only admit the one that minimize our function. But for simulated annealing, we have another condition that we can still make the move, even though it is a worse state. The probability is based on the exponential of the delta F and the temperature in here. Okay, and we iteratively to calculate to move the states one by one to search the solution. And along the way, we will also update the temperature. Slow the temperature. This is where we tune the temperature. But the actual value, it is application dependent. Okay, depends on your application. So the main objective of this algorithm as compared to hill climbing is we want to avoid to get into the local optimum. Just involve some stochastics in the algorithm, some randomness in there. Okay? Okay? Is that clear? Is that clear? Okay. So still, remember we have a similar landscape of using hill climbing, right? So in here, if you use hill climbing, you just stuck in here. So right now, if you use simulated annealing, or even though you're stuck in here, there is some chance that can uphill, but still you can make the next move based on the probability. You can go up and continue to till the minimum, right? So is that clear to you? This is the main of motivation of this new algorithm. Usually when we talk about research papers, one is what problem you're going to solve. For example, this is searching, right? Searching optimum solution. And then we have your motivation of this paper is can be published. Usually we say, why your paper is good enough? There's some contribution there. You solve some problem that existing paper could not solve. For example, hill climbing. They will get into the local optimum. But right now, we are going to avoid this problem. Then we can come up with a new paper. This is simulated annealing. You solve the problem and get stuck into the local optimum. Okay? Okay? You can say that is a setting point of a new work. That is the main part. Accept worst state with some probabilistic probability. Okay? Okay? And this one example, usually you can use simulated annealing to solve it. And this traveling salesman problem, any of you haven't heard about this problem? Many real applications, they fundamentally to solve this traveling salesman problem. Last week, we also mentioned a little bit this problem, right? We have a bunch of cities. Right now, assessment want to visit each city just once, and only once, and return to the first city that began the route. This is also an optimization problem. You're going to find the best route. Then you can use simulated annealing. And there are actual applications. For example, critical distribution for logistics, vehicle routing, supply chain management. For example, right now you are pizza deliverer. You're going to deliver pizza among the different regions. And right now you want to minimize your cost, the time, the transportation cost. Okay, so this is one actual applications. And let's take a look at one animation in here. So there are two things. One is the energy, your objective function value. The other is the temperature. You are tuning, just slow with the temperature. Get it slower. When the temperature is lower, then you have the high chance to reject the worst move. Because we believe that along the optimization, we are pretty towards the ultimate goal. So at that time, we just reject the worst action. At the beginning, there's some chance there. So at the beginning, the temperature is larger. Okay? Okay? So this is basic idea of simulated annealing. All right? Okay, let's take 5 minutes break to assess this part. We have a second part. Okay, that will be more mathematical dense. So take 5 minutes break. I come back.
就是刚才你说的那个 size，就是它那个 temperature，我们如果去 update 它的话，是只需要给它成一个就是常数系数就行了，是吗？每次都
对，你就改变它。对。
然后还有一个就是，就我们说到那个概率，算出那个概率，你怎么知道？就是那个它的 worst 的那个，它是在那个概率内的，就是你怎么用代码来体现这个？
就一个 random，如果要实现工程的话，做一个随机概率的。
我知道，比如说它概率做50%，然后我就在这个把这个做一个 random，然后它就可能在这个50%里，或者不在这个50%。
对。
哦，但是这个 random 跟这个本身的算法就没有关系了。
没关系，没关系。但是它就是确实要加入一些随机的东西，让它就像那个机器学习一样，它都会有一些随机性，让你没有办法去找到它的这个可行性。对，
就是它优化的地方，它优化的是什么？
优化就是我原本不是确定性的，我只要好我就等，我就用。那现在是我不好，我也有机会用。
但是就是为了去造那个 local
optimal，对。So let's continue our second part of today's lecture. Okay, genetic algorithm, as this name implied, genetic involves some natural selection. The idea is basically come from natural selection. So before we get into the algorithm, let me just introduce a little bit of some terminology. Okay, so this genetic algorithm is also a search-based algorithm that is based on natural selection from bioinformatics, biology. And this can be used for solving AI optimization problems. Here are some very important terminology here. Population. Population, it is a subset of all the proper solutions that can solve the given problem. You can think of that as a solution pool, a set of possible solutions, just a subset. And a chromosome, that's one particular solution. We name it a chromosomes. And usually because that is a string to represent this chromosome, so we also call that as a string. That's one solution. A particular element, we call that as a gene. Usually a chromosome can be a multiple bits there. One particular bit, that is one, we call that as gene. Okay? And fitness function. Fitness function, that is correspond to the cost function. It tells how good a solution is. It is used to evaluate the solution. Okay? And genetic operators, the basic operators within this algorithm, also main operators we need to design. One is mutation operator, crossover operator, and selection operator. These are three different components we need to tune, we need to design in this algorithm. There are three core operators. Okay? And the basic flow, we're given a subset of solution. We call that is a population. We select. And then each solution is a chromosome in here. And with each solution, each chromosome, that is a string. We have multiple genes there. We can do crossover to generate new offspring. And the mutation, we change a little bit some particular gene, what we call mutation. Okay, okay. And so in here is a animation. We can given a set of solution in here, P1, P2, P3. There are 3 possible solutions. We can evaluate that, the 3 possible solutions with a fitness function. We can evaluate how good it is with this fitness function. And given the landscape of this our objective, we are going to achieve some maximum. Okay, still, that is some variables. We are going to achieve the maximum in here, given this landscape. We can evaluate the how good of each particular chromosome, how good of particular solution. And there's a circle in here, roll rate, plot. We can do selection to undo crossover and do mutation. We have a new generation, iterative to get our ultimate goal. So basically, we have 3 components. Evaluate to select a bunch of solutions. And then, given this bunch of solutions, we do crossover to generate some offspring. We mutate a particular gene there, and then with iterative to evaluate the solution again and again. Again and again. Okay. If let's look at a particular chromosome here. This is assume this is one solution, right? We can evaluate in here. We just define there is a number in here. This is the probabilistic of this roll rate selection. The probability will be selected. Then we predefine a selection function. And this is a second solution of among this population. And we can get a cost function that with a sexy probability that we can generate new offspring. Basically, this genetic algorithm would like to give the good chromosome that with higher chance to generate new offspring. This is natural selection. If that is a good gene, they'll be used to generate new ones. Okay, so if you look at, suppose we given a population, we have 3 chromosomes in here, right? We can calculate the fitness value because this one with the 60% of higher chance to get selected. So it occupied a larger space in this circle. Once you rotate this circle, you get a high chance to get into this largest one, right? And you pick this one as one of the parent. Parent of P2 is in here. And we just pick a cut point to cut into 2 pieces. We change the parents. Assume these 2 parents. We have each parent be cut into 2 components. We just recombine them together. And then we can generate a new one. So why we do that? Why we do that? If you look at the terminology we introduced, population is just a subset of the solution. That haven't covered the entire space. You only do this combination, you can explore some solution we haven't in here. You can do mutation to explore some solution that we are unknown. That one toward a more universal searching space. Okay? Okay? So this is the basic idea. This is the basic idea. Let's take a look how we do this one by one. One by one. Okay? So assume we have 3 chromosomes. We have the 3 chromosomes. This is population with size 3. So we have 3 chromosomes. P1, P2, P3. This is one solution that we encode with this gene. Okay? We have 3 possible solutions in here. And we use the fitness function to evaluate how good is this particular chromosome. If it is higher, means it is better. So because P2, we have higher score, then this P2 is a better solution in this round. Okay, this is for selection. We have used this fitness to do selection. Because P2 has a probability, so we very easy to get P2 as our parent to do the crossover, right? Because this is a good one. We want to, as a parent, to generate a new one. That's why we have possible we pick 2P2 in here, because that's higher chance. Because P1 is pretty low, in here we just discard that. It is very, very low probability to be selected. So in this round, this P2, P3 are selected as the parents. And we want to generate new ones. How? Do crossover. In here, we just cut a particular point into two components. First component of P2. Second component of P2. P3, you also have two components. And we just recombine them together so we can generate a new one. This is our new offspring, right? Our new generation, our new possible solution. So this is for crossover. But still, we need to do mutation. This mutation, because remember, the population is just limited of solution pool. We do mutation, we want to explore something we haven't known in this iteration. That is get us high chance to explore something good we haven't known in this round. This is why we do mutation. Yes, you can design in here. Later we will show you in these three different components. You will have design your strategy. So you will have more parameters in here in this particular algorithm as compared to simulated annealing. Simulated annealing, T is something that you need to tune. But for genetic algorithm, you will have more components to design. Of course, this is also application dependent. Depends your application scenario. So far, so good? So far, so good? So far, so good? So one piece of information I want to convey to you is why do we need do reproduction? Because right now, genetic algorithm at the initial state, we just with a limit population, limit possible solution. Possibly, our best solution is not in here. We just given a limit once, right? And then we need to, based on these initial ones, we want to generate better ones. Based on what? Based on this fitness function. This fitness function guide us because it is higher, means that a particular solution has a good chance is our optimal solution. It is higher, then it is possible to be used to generate new solution because it has good gene. Okay? If you don't have the mutation, we just limit with these elements, with these genes. We don't have the possibility to explore the genes we don't have in this population. So that's why we have this mutation process in here. Okay? So this is a design intuition of this genetic algorithm. We have three important operators. Reproduction, we also call that is selection, crossover, and mutation. Three operators that are the core of genetic algorithms. But the idea is simple. The idea is that we use a fitness function to guide us to generate new solution with good genes. Okay, this is the basic idea. All right. Okay, so let's take a look at this flow chart. This is more from the structure, the entire flow chart of the genetic algorithm. You can also take that as a pseudocode. We have initial population with a limited amount of population of limited amount of chromosomes. Okay, given this, we evaluate how good they are. Based on how good they are, we do just pick the one with good genes. The higher means that that solution has good genes. And we use that parent to generate new offsprings. So we have the crossover and do mutation. Of course, this is to optimize this algorithm further. We want to just use the elite individuals. This is one more step to optimize the algorithm until we get the best chromosome bound. Okay, this is the basic flow of genetic algorithm. Of course, later on, we will introduce one by one. How do we design each component? What are the possible strategy for each component? How do we design a crossover operator? What are the possible mutation operators? Okay. Okay. So of course, whenever you have an algorithm, you have a problem. How do you adapt your problem into this algorithm? That means how to represent your solution into a chromosome. Right now, we're talking about chromosome, a string. But how do you represent your solution into a string? This is the first step. Whenever you're doing deep learning as well, if you are doing NLP, natural language processing, you will have represent your text, your language into a sequence of numbers, representations. Whenever you're dealing with image, you will have to represent your image into a sequence of strings, numbers. This is data representation. As the same in here. For genetic algorithm, we also need to represent our solution with a string, chromosome. And each particular element, that is a gene. Okay? That is also application dependent. And we can, so in here, we also have for each gene, for each chromosome, we will have a fitness function to evaluate how good it is. How good it is. So basically, we need to come up with a solution to represent an individual as a gene type. If that is a binary, decimal, real number, or order based. Okay, and with this string, how do we evaluate if that is good or no? This is a particular fitness function design. Okay, okay. And so let's look at this binary one, this sequence. Just a sequence of number. And each bit, it can be 1 or be 0. That is a gene. As I mentioned, each element of the chromosome, that is a gene. And here is a binary representation. And so, what does this mean? If given this kind of binary representation, it can represent an integer. What's the value of integer? If that is a binary, what's the value? What's the value? Binary to the integer, the actual number, right? There's something that in familiar ways. So you can use that one string to represent one particular value. This is how we use a binary to represent the integer. You can convert, right? So that is, in other words, in here, we use a 8-bit gene type to represent this actual number. In your problem, that can be a solution, right? If that is actual number. All right, all right. So basically, with these 8 bits, we can represent the value from 0 to 255. This is a range of this binary representation. Okay, okay. So this is for one parameter. If we have 10 parameters, then we have 10 bits. You have 10 bits. This is a data representation. How to represent your solution. So we can continue to use this genetic algorithm. Okay, okay. So what if right now that is not an integer? If that is, we use this 1, 2, 3, 4, 5, 6, 7, 8. This 8-bit sequence to represent a number from 2.5 to 20.5. So what's the actual value? What's the actual value of this sequence? 1010011. This actual number, if you convert it into integer, that is 163, right? And because this entire from 000 to 111, that is represent 2.5 to 20.5. So here's the way. For this string, what's the value? Just use this formula, starting point. This is the actual value of this 8 bits sequence. This is the range. This is the actual value of convert this binary string. This is how we represent our solution into a binary string. Okay? 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 So what about if it's 000? So what's the value? Quick. Huh? 2.5, right? What about 1? 20.5, right? This is the smallest one. This is the largest one. So this is how we use binary representation to represent your solution. And so there are some important for this mutation. Whenever you do mutation, of course, after mutation, it should be valid. Like if you change the elephant, whenever do mutation, still that is an elephant. That's what we call valid solution. This is a basic requirement of doing mutation. Okay, as I mentioned that the mutation basically want to explore other the search space, explore a solution from outer space. This is the motivation of doing mutation. And you can do binary mutation, just flip. If that is just binary, doing flip. Okay, bit flipping. And so usually mutation with just a very, very tiny probability. Okay, usually it's a tiny probability. If okay, this is something I mentioned, the motivation of doing mutation. What's that? Is it important? Is it important? If you don't consider, what will happen? If you don't consider mutation in genetic algorithm, if we only consider selection, only consider crossover, what will happen? No co-optimal. And there's no way you can explore other possible better solutions. It's just limit the gene because this pool, this population just limit solution there. If you are doing mutation, you can explore most possible solutions. Okay, this is why we need to mutation. And here is the, if we, for the order base, just now we mentioned a binary one. And this sequence is a order-based representation. Each bit, they are mutual, they are different, and they are ordered. They are from 1 to 8, but in different orders. This is order-based representation. So if you want to do the mutation, you just flip 2 particular positions to generate a new offspring. This is for order-based representation. Okay, so that means if you have different representation, you will have different mutate operators. Okay, for binary, just doing flipping. For order-based representation, you just pick 2 particular position and just change them. This is how we generate new offspring. Okay, and for tree, we talk about binary representation, we talk about order-based representation. When you use the tree representation, if this is one solution, this is another. How do we do mutation? We just change the corresponding operand or operator. This is one parent, right? You can do a particular, this operand. Then if you're doing operation, you just change this operand into another operand. Because you need to make sure this is valid. This is a new valid offspring. If you are doing the mutation over the operator, then you will need to use operator to replace it. This for tree-based representation. So in here, you can see with different representation of solution, you will use different mutation operator, case by case, okay? And crossover. So while we do crossover, we pick the parents. The parents will occupy a particular gene. And we just pick the parents together and just pick one component of one parent and another from the other parent, and we combine them together. These parents, they are selected based on the fitness function. The fitness function tell us how good of this particular parent contain good genes. Then we can use their genes to generate new offspring. So this is crossover. So in here, you can use a single point cut. You just cut into two pieces. And we have two parents based on these cut pieces. It's just recombine them together. Then we can have new offspring. Of course, the same constraint. The new generated offspring, they should be valid. They should valid solution. Otherwise, we do not need to evaluate over that, right? At least you should make sure the generate offspring, they are valid. Okay? And this genetic algorithm want to inherit the good genes from parents. So we will need good selection policy. How to select the good parents to do crossover. This is selection operator. Okay, of course, this is just one particular crossover operator. You can do some uniform crossover. This is different from the single point cut. You can also use uniform. For example, we have two parents in here. And right now we want to generate two new offspring. And for each bit, we have the uniform probability. We can just select, okay? If that is 0, we do not do. We do not need to do the crossover. But for the bit with 1, we just do crossover. With this policy, we can generate a new offspring. This is what we call uniform crossover. Okay? Okay? So this is a uniform crossover. And for order-based representation, how do we do crossover? There's another policy. There's another policy. How to do this crossover? First of all, choose an arbitrary part from the first parent. And these are first parent. Assume we choose first part 1A2. We just fix it. That is one part of the offspring. And copy the remaining genes from the second parent because this is order-based. For the offspring, because it contains 1A2, we do not need to consider 2A1 here. We just consider the rest of them. And we just copy the starting right from the cut point of the copy part. 4, 3, 6, 7, 5. These are recipes from parent 2. And we starting right from the cut point of the copied part from in here. We use the order of genes from the second part. 4, 3, 6, 7, 1, 5. And wrapping around at the end of chromosome. Wrapping around here. Repeat this process. So what's that? What's that? Still, we use this example to illustrate how it works, okay? So we are the parent 1. We copy one component 1A2 from parent 1. And the rest part, that's 4, 3, 6, 7, 5 from parent 2, right? And this is the rest part from parent 2. We just get started from the right of the cutting point of parent 1. And ramping up from the beginning. That means we just put the sequence of the number, put it here. Starting point, right off the cutting point. Press 4, 3, 6, 7, 5. This is how we generate a first child. This is how we generate first child. So this is another way of doing crossover. So you can see for mutation, for binary representation, for tree, for order based, we have different type of mutation operator. And for crossover, the same thing. We can design different strategy to do the crossover. This is just something that the process you can do the one way to generate an offspring. But just copy one part of genes from parent 1 and the other part of genes from parent 2. This is how we generate new offspring. So for child 1, we have this, and what about child 2? With this policy, how get child 2? What's the value of child 2? Where's the child 2? Just guess. We copy one component from one parent, and then we copy the rest of part sequentially from right hand side of this copy component. Right? So we get starting from 2 and 6. Right? 2 and 6 in here. And 2 and 6, 7, 3, 1, 4, 5. And will be 2 and 6, 7, 3, 1, 4, 5. We'll step back from the beginning. Right? Yeah, this is a way to generate new offspring. Okay, so this is how we get the child. And for a tree, we just randomly pick the subtrees to create combination. Here we have these subtrees, subtree by subtree. This is just how we represent a mathematical calculation. That can get solution, right? That can be a solution. You can do mutate operator over one particular operator for all operator. You can do combination with the pick any subtrees. That's right. We generate new offsprings. Okay. So right now we have discussed about some possible strategy doing mutation, some strategy doing crossover, and one part. How do we select parents? Remember, the core idea of genetic algorithm is to select the best possible genes. So to reproduce our best possible solution. Right? So we want a way that bad individuals have a better chance to being parents. So we can inherit the genes from the parents. This is our intuition, right? And give us the selection pressure iteratively to fill out the solution. We want to maintain useful genetic materials. There are some popular selection algorithms, for example, raw rate Wheel selection. This is something we have shown you. The plot, that is raw rate Wheel selection. We use the cost function as our probability. If that is larger, that means we have got a chance to get that particular chromosome. The region is larger. This is raw rate real selection. And we also have rank selection, tournament selection. There are many different variations of genetic algorithm. If you just search genetic algorithm, there are tons of papers. There are papers that talk about different mutate operators, crossover operators, and selection strategy. They together to come up with good solutions. Okay. So this is raw rate prep. And we can design this kind of Phillips function to decide for each particular chromosome, you can occupy a particular region. You just rotate to randomly pick the one. Of course, if the region is larger, if the value is larger, we have the higher chance to get that particular chromosome as our parent. Okay. So in here, we define a fitness of this xi. This xi is a particular chromosome. F bar is the total fitness in the population. Of course, if fitness is higher, it means that it contains better genes. We have a better genetic materials, and we want it inherit to the offspring. Then it can have a chance to get selected. So they occupy the larger space in here, right? So this is how the raw rate real selection mechanism. What if we have a Phillips function that all the chromosomes, they are evenly distributed? What will happen? There are two extreme cases. One is only one or two selections that occupy most of the regions. That means a particular chromosome is extremely case that extremely good occupy the largest region of the raw rate wheel. What will happen? They converge very quick because always like this chromosome, and we lose the diversity, right? And the other case is that all the solution chromosome, they are evenly distributed. But we very easy, they are very similar to each other. Then we're easier to get the local optimum. So this is the downside of genetic algorithm. They very depends on these three function design. Do not match these two extreme case. Okay. These are real cases, edge cases. And the other design, the red bullet points, remember, this one other optimization strategy, that if you want to make the good genes to be inherited, then whenever doing selection, you always keep the best 10% of parent. Okay, just want to keep a 10% of parent and leave out the worst one. This one strategy that make the algorithm converge faster, to easier to get the better solutions. Okay. And so this is our three main components of designing genetic algorithms. Three main components. And how do we stop? Remember, we have the populations. We're doing parent selection. We're doing crossover. We're doing mutation. And then we do generate new population iteratively. But when do we stop? We have the stopping criteria in here. When we have achieved the optimum, or we consume up the resources, like we set the maximum iteration steps, right? And this is when we doing stop. Like when you are doing training the machine learning system, the same thing. There are something that make you to stop training. This is a stopping criterion. Okay. Either you just constrain, you just run how many iterations based on the computation resource, or when you reach optimal. Okay, so this is a basic stopping criterion. And so these are some of the advantages of genetic algorithms that can do parallel computation. You have a bunch of populations you can do separately, right? You can separate the population into different components and combine them together. We use distributed computation in these genetic algorithms. And of course, especially if you are talking the deep learning era these days, usually I think the most important thing is that we don't need large amount of training data. This is the one main advantage as compared to the deep learning models in these days. Okay, and we do not need to differentiable constraints because we didn't talk about gradient here, so we do not need to constrain the Phillips function that is differentiable. Okay, but the problem, there are some problems. If we look at the genetic algorithm, there are 3 different components you need to design. We have too many hyperparameters to design. As compared to simulated annealing, one thing you need to design, you need to choose temperature. But for this genetic algorithm, you will have to well design your selection strategy, your mutation operator, and your crossover operator. And each of them has a randomness. Okay? And also the quality of final solution is not guaranteed. And one thing is also that usually computation intensive. And usually they use this algorithm to solve the hard problems. Okay. So far, so good. So the basic idea of this component is that genetic algorithm is an optimization for solving problems, of course. And we have 3 different components to design. First of all, solution representation. Based on this, you need to design the mutation operator, the crossover operator, and the selection strategy. The basic idea is to use this Phillips function to guide us to select the best possible genes, to guide us to get to the optimum solution. Okay? So this is the basic idea of this bunch of introduction. But how do we know this genetic algorithm works? How do we know? The idea is there. Of course, we select the Phillips function to generate good genetics, to inherit good genetics into the new offspring. The process, the idea is there. But how do we rigorous to illustrate why it works? At least we need to make sure after each iteration, our solution contains better genes. Right? How do we make sure? So this is what we're going to illustrate, the schema theorem. That part is also important. I'm saying important means that they may appear in the exam. So something that you probably need to consider. That I say important, okay, in terms of that. So the following I will illustrate how do we rigorous illustrate why genetic algorithm can lead us to good solutions, even though the optimal solution may not be guaranteed, but still iteratively they can reach something that is better and better. Okay. So let's take a look at the population in here. This string, a bunch of string, they are a bunch of chromosomes. Each one represents a solution. And we have their objective function value. If you want to achieve a maximize objective function value, of course, you can cheat. This chromosome possibly is a better one because it has a good has the best objective function value, right? So this is a list of strings. Right now, we use a simple coexample. Just use this binary representation. Each of them is a chromosome. Each bit is a gene. So far, so good for this slide. Okay? And for schemata theorem, what is a schema? Schema is a set of strings that share certain values. Certain values means they share certain patterns. They have some common patterns. Still, look at these three schema. They together, they share the patterns of this first column. Star, star, one, star, star. Star means they can be arbitrary bit, can be 1, can be 0. Okay, this star means, and 1 is here. So means you can see for these three different chromosomes, we are all share this one pattern. They have one fixed bit, that is 1 in between. Right? And for the first and last one, we share 2 positions, they are fixed 1. This is schema that shared by these 2 chromosomes. And for the first 2 chromosomes, we share the same pattern. The first bit is 1, the third bit is 1, and the fourth bit is 0. This is the schema. Means they share the same pattern. Okay, is that good to you right now? For what is a schema? Share some pattern. You can think of, given a population, there are a bunch of solutions. There are something that in common. We just define they share some certain patterns. We call that is a particular schemata. Okay, that's a particular schema. And so for this schemata theorem, we want to understand the more rigorous term to examine the growing rates of the various schemata or similarity templates. So for each schema, you can see that is a particular pattern. That is a particular templates. Okay. Here we have some concepts, some concepts. A schema match a string if at every location the schema, either 1 or 0 or star, they're the same. We say that is schema. They share the same pattern. Okay, there's a particular pattern. And for cardinality, K, there are K plus 1 over L schemata. This L is the length of a string. And the K is, if we're talking about binary, that is 2. K, that's binary coding. Okay, then, for example, for a 4-bit, a length is 4. How many schemata? What's the possibility? For each bit, there are 3 possibilities, 0, 1, or star. The length is 4. So total, there will be 3 multiplied 3, that's 3 over 4, right? That is 81 schemata. That for this case, you can say that is 81 schemata. You can treat each of them as a possible solution that can occupy, right? And also we have 2 more important definition. Later on, we improve lower order, lower defined length. We get us a better genes, a better ones. We prove that iteratively, with a new generation, we inherit better genes. There are 2 important definitions. One is the order of schema that defines the number of fixed positions. And defined length is a schema that the distance between the first and the last specific fixed positions. Let me show you 2 examples to see what does that means. Okay, for this the first schema is 1. S2 is another schema. And for this one, the number of fixed position, how many? 4. Star means they can arbitrary though, so we will not set as fixed. Only that is 1 or 0, we set as fixed. So for schema as 1, the number of fixed position, there are 4. For S2, that is how many? How many? 2, right? This is the order of the schema. Means the number of fixed positions. And the second definition, define the length, ds. A schema is a distance between the first and last specific fixed position. The length, the distance, the first and last. So what's the ds in here? So what's the distance of first and last? 1, 2, 3. That is 3. The distance of 1 and 1. That is 3. The first and last specific fixed position. The first fixed position is in here, 1, right? The last one is in here. So what's the distance? 3. 1, 2, 3. The distance of first and last fixed position. For this one, for first and last, what's the distance? That is 5. So because these variables we'll use later on, I introduce in here first. We use to improve the particular mutation operator, the crossover and selection. Each of them will give some probability of that a particular schema will survive after each iteration. Okay? So far so good? So far so good to the dense information. Later we can come back, okay? Let us go through first. There's some preliminary information you need to get. And then we can get into consider the formal definition, rigorous proof of how genetic algorithm works. Come back later for this definition, okay? You will see how it works, why it's important for our proof later. And so let us consider the individual and the combined effect of genetic operators. Remember, we have 3 operators. Let us consider the selection first. So in here, we define a fitness of schema equals to the averaging the fitness values of all strings in a population that match this schema. This is for specific schema. S. We define this is the averaging the number of strings match schema in the current generation. So in the current generation, among this population, the subset, among these solutions, right? We have a particular schema, a particular patterns. We want to evaluate the importance, how good this pattern. So right now, use this fitness function, this averaging the fitness values of all strings in the population that match this schema. Means that this function used to evaluate the importance, how good of this schema among the population. Okay, so far so good. So this is our first definition. We will see after iteration what's the possibility of this schema will survive. Will survive. Okay. And if we want to consider the I string is selected with a probability. So the probability of a particular string, a particular chromosome, what's the probability? We have n total number of strings in the population. This is the fitness of this particular chromosome. Remember, this fitness is to evaluate how good the possibility of this particular chromosome will be selected, right? So in here, among all the population, the probability of this particular chromosome will be selected as PI. So the definition, so far so good. The meaning of these two formulation. This is to evaluate how good of this particular schema with this formula. This is the probability of a particular chromosome will be selected among the n populations, among the n solution among in the population. Okay. Then, if we want to take a look at how the xi to be selected, we just calculate this particular chromosome. What's the probability? Just occupy, divide by the total among the population. This is very intuitive, right? Intuitive. Among the population, all of the fitness is calculated by the combine of them. This is the value of this particular chromosome. So if we want to select n, what's the probability? We just use the rotate wheel. We pick n times. So the probability of this particular chromosome will be selected. That is n multiplied by chromosome. So good for this probability calculation. Each time this chromosome being selected is calculated by the fitness value. We do n times, right? So among the population of size, this chromosome is being selected. That is n multiplied by this pi. So far so good? So far so good? Okay? Okay? And so the number of strings matching the schema in the next population. Okay, this is something we want to take a look at. Remember the core of what we discussed so far. We want to prove using genetic algorithm, we can eventually to get a good solution. This good solution contains the good genes. The good genes means that a particular schema with good fitness value, right? So we want to compare for next generation of this particular schema and the current generation, the number of this schema survive. If that is good enough, that be increased. This is the core of this, what we're going to do right now. We want to see for next generation and current generation, if that schema have a good fitness value, it will be increased or no. This is the core, what we are looking at right now. What do we want to prove right now? As long as we find out the schema fitness value is large than average one, then we will think that is a good schema. Then we want to make sure with this iterative genetic algorithm, it will be survive. That means with the iteration in here, this one should be larger than one. Let's see, okay? For this is the next generation of a particular xi being selected. The number of strings matching schema S in the next population equals to n multiplied by this overall fitness value. This is a schema fitness value, right? So far so good? For this one? And this equivalent, we just put R and R here, this is equivalent. We put N over in here, they're the same, right? They're the same. And what is this component? This is the average schema, this is averaging. Fitness of, this is the averaging of the fitness of population. This is the average fitness of the schema. Also, we call that importance of the schema. And this is the average fitness of the population. We just replace with this notation in here. So remember, what we want to do is want to calculate the schema if that be survive after a particular iteration, selection in here. The first component in here is the total fitness of string matching this schema. This is also the overall. Assume with this population, we find out a particular solution that matching this schema. Right now, this first component, we want to prove how good this schema. And this is the overall. All of the solutions among the population, we calculate all the Phoenix value. So far, so good? No. So far in here is good, right? So here, is that good? Calculate a particular strings being selected among the population. Right now, we just consider the selection operation, the selection component. We want to take a look at the survival of particular schema. Survival will be inherited from iteration. Because ideally, if we say this genetic algorithm work, that means we say the good schema, the good patterns will be inherited, will be survived. That is our goal, right? So right now we want to prove that is true or no. Only it is true. That means genetic algorithm always can towards a good solutions. Always can inherit the good genes. This is the basic idea. So this term, is that clear to you? This term, for first term. This is calculate all of the solution that matching the schema. We have R among the population. We only have R solution that contain a particular schema. A schema is a specific pattern that contains some fixed position and some star. That is a schema, right? That is a particular pattern. Is that clear so far? Okay. And we just divide by the total fitness of all strings in a population. We want to take a look at if the number of strings matching schema in the next population. We have n, because each population, we will select n solutions, right? N samples. That's why there's n here. Okay. Okay. So we want to take a look for this generation, this new population. What's the percentage of this schema occupy the overall? This is what this means. And for this one, it's just simply doing some math calculation, some math conversion. You put n in here, that is equivalent. Put r, one r in here, one r in here, that is equivalent, right? So this is the all fitness value divided by n. This is average fitness among the population. And this one is the average fitness of the schema. This is something we mentioned before. So this is this average fitness of the schema. This is the average fitness of the population. Then we have a ratio in here, that is R. R is a number of schema matching, number of chromosome matching schema. This is R, remember? And this is the schema matching in the previous generation. That's why we call this is NS, this is T, the last iteration. This is current iteration. So we can get the current number of strings matching schema S equals to the previous generation, that matching the schema in here. And there is another term. This term equivalent to the average fitness of the schema divided by the average fitness of population. So as long as the schema fitness is larger than the average fitness, means that is good than average. Good than average means that will be larger than this one. That will be larger than 1. This will be larger than 1. Means as long as the schema is good, it's good, better than average, then it will be survived because this is larger than 1. Is that clear? Is that clear to you? The basic idea. Okay, let's go back to fitness value. That basically to evaluate how good a particular chromosome, a particular schema is among the population. So right now we have these two terms. The T plus 1 iteration, the number of chromosome matching schema is in here. It is equivalent to the number of chromosome matching schema multiplied by this term. This term is the average fitness of a schema divided by the average fitness of population. So as long as this one, the schema is larger than average, better than average, means that it's a better genes that we want to keep. Then this one is larger than 1. Then larger than 1 means the schema can survive. Okay? As long as it's larger than 1, then we can just use a small tiny value to represent it. And we can represent the different iteration with a 1 plus a very tiny value and the previous iteration generation schema matching. As long as this is larger than 1 means that it will be survive. This is guaranteed. Okay? So the basic idea of this slide is that right now, as long as the schema, we have the fitness value that is larger than average, that means that is a good one. That good one, we want it to be survive. And in here, as long as this is better than average, this term is larger than 1. Larger than 1 means that this the T iteration, number of schema, number of chromosome matching schema will increase along iterations. That means it is survive. This is the basic idea. Is that good? Is that good? Quite dense today, quite mathematical dense today. So this for selection. Yes? Y R equals to which one?
NS times T.
N S times. Oh, this is R. R, the definition of R is a number of chromosome matching scheme. This is a definition of R. And so given this population, we can calculate R. R chromosome matching scheme have contain this pattern schema. The number of R is in this iteration. Predefined. And then for the next iteration, we have no idea how many it is. So right now, based on the constant we know, it is multiplied by a ratio. Let's go back to a little bit. R is a number of strings matching S in the current generation. They are the same, right? And for the next generation, right now we prove that it is equal to the current generation, number of current generation multiplied by a ratio. This ratio, as long as larger than 1, means that the fitness of the schema larger than average. Then we want it be survive. Then it is larger than 1. Then it will increase. The number of the schema will increase. Right? Yes. Because the fitness value already tell us that is a good one. Then we want to be survive after the next generation. Okay? Okay? So this is a selection part. Why? We see that it always larger than 1. That means as long as that is good one, it will be increased. Iteration after iteration. Okay? And let's take a look at the crossover. Crossover. Remember crossover. We have 3 operators. We have selection. Now it's crossover. Still. For assuming that the crossover point is uniformly distributed across the string. So for string, we have different places to do the crossover. The cutting point uniformly. The probability of destruction of S depends on the length of schema. Remember distance of S. That is the first bit or last fixed bit, length, the distance, right? Then these are 2 fixed points. If we want to destruct this schema, what's the possibility? ds divided by L minus 1. Whenever you put a cut point in here, in here, in here, you always can destruct this schema. Okay? Is that easy to understand? Right? Remember that ds is a define the first and last fixed bit, the distance. Look at this example. This is the first bit, this is the last bit, this is the distance, right? So as long as you put the cut point in here anywhere, you can destroy this schema. So the probability of destroying this schema is ds divided by L minus 1. Okay? Then we can see the probability of survival. 1 minus this destruction probability. But remember, we have the crossover probability. So we can multiply the crossover probability to define the probability of a particular schema survival for a crossover operator. So this will be easier to understand, right? It is better because we know the ds in here. Anywhere, any places doing the cut, you will destroy it. And if we want to survive, we use 1 to minus it. Because crossover, we have a probability. So we probability multiplied by this destruction probability. Then the ultimate survival probability is 1 minus p crossover multiplied by ds divided by L minus 1. This is how a schema is survived with this crossover operator. So we're always talking about survival, right? And so put them together, multiply this probability together. We can combine the selection and crossover, how the schema will survive. And for the mutation, doing mutation. So with the mutation probability, the survival of schema is equivalent to, remember what is OS? OS is the order of schema. The number of fixed points. Number of fixed points we consider. Remember, the schema, the order. So as long as we're doing mutation over these fixed points, we're doing mutation, right? This is we're not doing mutation. We then keep the survival. This is the order, remember the order? So assuming this is larger one, we do approximation. This approximate to 1 minus P, this is the mutation probability. This is survival. This is survival probability. OS is the fixed points. We do mutation. And if we want to survive, we do not do mutation. 1 minus the not do mutation probability. So this is how we make the schema survival, right? Approximate 1 minus PM multiplied by OS and put them together. We have these terms. 1, 2, 3 for selection, for crossover, and for mutation. This is how the number of chromosome matching schema in this current generation. For next generation, how it get there? Multiply these different terms. Okay, that means we have a shorter defined length. This is shorter. This order is lower. Then we have a larger probability. We have a better Phillips function. We have a larger probability to survive this schema. Okay, so was it good? This component from the selection operator. This component from the crossover. This component from the mutation operator. Put them together, we can see the number of chromosomes matching this particular schema, the number depends on this bunch of values. Only when this bunch of numbers larger than 1 means that particular schema will survive after each iteration. Ultimately, they will survive. If it's larger, then it has a higher probability to survive. Right? So was it good? Then we need smaller defined, shorter DS, smaller order, low order of this schema, and higher finish value. Okay, this is how genetic algorithm works, with a very rigorous proof, considering selection, crossover, and mutation operators together. You can see we have a bunch of different randomness. Randomness in mutation, randomness in crossover. So as compared to simulated annealing, it is more complex. We have more scheme to design. We have more parameters to tune. That is more complex, but the solution more robust. Okay, if you check, there are tons of papers talking about different variation of genetic algorithms. Okay, okay, very dense mathematics today. That's for all. Okay, okay. Take 10 minutes break and come back. We have a tutorial.
Okay, so maybe we can check the answer together. uh, the answer should be also this time involves some more calculations, but it should be also easy. For example, the fitness of solution 2 is 576 over the sum of the all fitness values, and it should be 0.49. And similarly, you draw the pie chart and draw the line, or you compare the probability with the random numbers. And this time, still, the solution 2 and solution 1 will be selected. But you will find that two selection strategy will induce two different probability pie charts. And this time, it is a coincidence that the same random numbers induce the same selection. But maybe if you choose another random number, and within these two selection strategy, different solutions will be selected. So any questions about this two exercise? Okay, if no, we continue to exercise 3. This is uh oh, this is an exercise about the new encoding strategy rather than binary. This time we encode the problem as the sequence, and the problem is two chromosomes ACDBE and ADECB are initialized for solving a traveling salesman problem. The distance matrix of the 5 nodes is given in the table. And the traveling salesman problem is something like, for example, ACDBE. It is the visiting sequence. You visit from A to C to D to B to E and back to A. And if your visiting solution is ADECB, so it should be from A to D to E to C to B, and also back to A. We do not apparently add the A back in the end of the sequence because by default you will go back to the starting point. So we do not denote A in the end of this chromosomes. But you need to remember to go back to the starting point. And with this encoding strategy, the mutation operator is to exchange the positions of two mutation points. For chromosomes ACDB, the mutation point is second point, and for chromosome ADECB, it is fifth. So if two chromosomes should be selected from parents and offspring, the parents are these two, right? ACDB and ADECB. And the offspring are these two, the mutated solutions. By rank weighting selection, which two chromosomes will be selected if the random numbers are 0.3 and 0.9. So any questions about this question about this question itself? If no question, you can try to solve this. Maybe we can have 4 minutes, 3 to 4 minutes to answer this. Okay, so maybe we can check the answer together. So first we evaluate the parents. For example, for the ACDBE, the code should be the AC plus CD plus DB plus BE, and remember plus the EA. We need to go back to the starting point, and you can look up the table and plug in the values and obtain the answer. And also for the parent 2, ADECB, the same. And for the offspring, and in the problem, the first offspring is the mutate points are second and the fourth. So we just swap the second and fourth point. The second is C and the fourth is B. So we swap C and B, obtain a new offspring, A, B, D, C, E, and similar. And for the second parent, we perform the mutate between the fifth point and the fourth point. So we swap the C and B, so we obtain the ADEBC and the similar calculate the cost. After the calculation of this cost, we can obtain the value tables, cost table as the 60, 98, 103, and 141. And the difference is here. This is a problem of the minimization problem, right? We need to find the minimal cost. So here, the large value, the large cost, we denote with a smaller rank. For example, the ADEBC has the smallest cost, but we assign it with the largest rank, the rank 4, and the 4. And for example, the ABDCE has the largest cost, but we assign the smallest rank. And then we calculate the probability table. And for the random number, 0.3 and 0.6, here we do not visualize it, but you can calculate first the 0.3. It is within the first solution, 0.4. So the first one will be selected. And the second random number, 0.6, it is within the second solution because it is smaller than 0.4 plus 0.3, but larger than 0.4. So the second solution will be selected. So any questions about the exercise 3?